So welcome to the first course of featured engineering and selection. This is a very interesting book from Max Kuhn, and he is, well known as Caret developer, Caret package developer, and many other packages. Tidy models, and so it's quite, an important figure within the model world. Then the other author is Kelly Johnson, so Kjell Johnson, and so he is very important. So we hope I invited them to join our book club, maybe for a session. So hopefully within the next session, we'll have some Q&A with the authors. All right, so welcome to all of you. I don't know if you like to do a bit of introduction of you, like a couple of minutes. Yeah. What do you think? Would you like to do a bit of interaction? Who's going to start?
Okay, I'll start. My name is Ricardo, and I'm based in Orlando, Florida. Mickey's land, Mickey Mouse land. And I've been, my regular job is not really data science. It's more appraisal. I'm machinery equipment appraisal. But, since my early studies as a bachelor in industrial engineering, I got acquainted with statistics and, statistical process and modeling. So I'm kind of, back and trying to do a career change in terms of getting more into business analysis and data science.
Welcome. Okay.
I'm Brandon. I'm in the Eastern time zone as well in the U.S. I'm closer to New York City, just in New Jersey on the other side of the river. I'm a research scientist. I do agricultural research for a vertical farming company. I've been using R since like 2009 when my previous company wouldn't buy me a SAS license. So I had to figure out how to do statistics on my own. And pretty much have been self-taught since then in terms of my R career and also statistics, which is a little scary. But yeah, I'm really interested in this feature engineering book because I'm curious what they're going to say about how to get the most out of your data sets in terms of those sorts of things. So really excited to be here. Thanks to Federica for leading and also prodding me to join as well.
Thank you.
Oh, go on.
Oh, go ahead, Will.
Oh, sorry. Yeah, in that case, yeah, my name's Will. I'm based in Bath in the UK. I've been doing a course with Federica, the Bayes Rules book, which is slowly coming towards the end of that. And I thought I don't want to finish learning, so I'm going to do another book, basically. I've been using R for quite a while. I had an undergraduate courses in statistics quite a while ago. I've done some Open University distance learning on postgrad level as well. But yeah, I just find it interesting, really.
Thank you.
I guess I'll go ahead. My name is Jim. I work in the Chicago area in Central Time in the States. I work for a large, say, global manufacturer, and in some ways challenged most recently in coordinating a sort of a center of excellence at this point So I get involved now with promoting sound, robust best practices and use of statistical tools, and some now thoughts like ML ops and being able to train models consistently, repeatedly, without issues like leakage and other crazy things. I get drawn in now to conversations with outside parties, consultants and others who they go fast, but sometimes take shortcuts. And so helping my colleagues in the business and others maybe understand what they're asking for, and you know, looking to advance what analysts in our different functional groups are capable of is all in my interest. I get involved in a little bit of education and a little bit of promoting things like books. And I have read this book. I'm keen on at least having a better understanding of what's in it to be able to package this and sell these ideas to our analyst and BI community, you know, at whatever level they're at. And so I'm excited about working with you all on the individual chapters.
Thank you.
Yeah, and sorry I don't have the ability to turn my camera on right now. My name's Ben. I'm a recent grad, 2020 grad in statistics, and my current role is right now in more of a data processing quality control. I'm looking to pick up some more skills in sort of the modeling aspect of things, so I can start gunning for maybe a more data science type of role. I feel like, you know, picking up the skills with just going through this book would be very helpful to me.
Thank you. Welcome, Ben. So we have an expert today. Okay, so I start sharing. And as you can see, so he is the other author, Max Kuhn, and they have written these two books, and applied predictive modeling is the other one, which is very, very interesting as well. Okay, so let's get started. So this, the first part of this book is not just an introduction, it's a real chapter. So even if just the preface tells you a lot about guidelines, about many things that will turn up very useful for you to understand how to modeling. Okay, so read it very carefully. Because there's many interesting insights. Okay, so the objective of this first chapter is to recognize the structure of the book, so understand how it's composed and what are the parts that we might be interested in more than others. Establish the baselines for good practice and define feature engineering. So what is it? The book is divided in two main parts. Okay, we have a feature engineering and feature selection. So feature engineering goes from chapter 2 to chapter 9. And we will go through some real world examples, review a bit of predictive modeling process, and you know, some exploratory visualization focused just on modeling, then encoding both categorical predictors and engineering numeric predictors. So this is a very interesting part as well. It's the core of featuring. So that's interesting. Then we will see things about interactions effect, and how to handle missing data. Then there is the last chapter of this first section, which talks about profile data. And these are data like time series analysis or image recognitions. So all those tricky things that requires a bit of more like feature engineering. Then the second part, which goes from chapter 10 to chapter 12. So the last 3 chapters are about feature selection. So you now have an idea of feature engineering. So you are aware about how to do the things. And you have your bucket of predictors that you have featured. And now you make a selection. So, and there is a little overview, and then a greedy search method and a global search method for selecting within your featured predictors. Okay. So this is the structure of the book. So good practice. Okay. So just to give you an overview of the little insight that you can find within the preface, the introduction of the book, is that there are some vital steps to take when you attempt to model. Okay, to achieve the best, the best model performance, and even if you to just featuring predictors, it's very important to have knowledge of the process that you are going to model. So if you have a bunch of data that you don't know anything about, so you need to do a bit of research. And so that's an important step, because you are going to spend some time looking at the data, understanding how they could be, what the response could be, and everything. So then collect appropriate data. If you miss any information, you search for the information, try to see if they are reasonable, the things that you got and everything. Then understand the variation in the response. So you now focus on the response variable that you are going to predict, and you need to investigate a bit more about its variation. Then select the relevant predictors, and then finally utilize a range of models. So, but what happens? All of these are not enough, because models performance can lack. Even if you do all this, you follow all these steps very thoroughly. So the answer for this lacking performance might be in the way the predictors are presented to the model. So feature engineering, what is it, feature engineering? So the definition in the book is the best re-representation of the predictors to improve model performance. Okay, so now we can use Cohort, we can use data wrangling, we can use tidyverse, we can use Bayes-R, but we are provided with a nice package, which is recipes. So recipes inside allows for a certain number of step functions, and there are other packages related to recipes with step functions, other type of step function, which they turn up very useful, and we mentioned that in the following sessions. So what are the possible way to achieve a better performance? So using feature engineering means transform the predictors. And we can do this transformation using special functions such as log or exponential or any other like special function transformations. We can add an interaction term like a product, ratio of the terms. We can add a functional transformation. So we can make polynomials, we can do splines, we can add a re-representation of the predictors. Like we do some statistics of our predictors and we use them as a features within our bucket of predictors. So then finally we can impute missing values with some other advanced techniques such as KNN or bagging, for example. But you know, you need to remind yourself that risk of overfitting doesn't go away. So, all right. So going forward, what is modeling? So when we do modeling, we can do modeling for a scope. Okay, why we do modeling? For making inference, for making estimation. So sometimes we know what we are going to do, but sometimes we are forced to choose between the two because of the data, because of the uncertainties. Okay, so if we do inference, simple models are better. If we do estimation, a bit more complexity is allowed. So the estimation of uncertainty and noise is another very important step to take. And the book says, if a model is only 50% accurate, should be used to make inferences or predictions. So the trade-off between accuracy and interpretability is very important. For example, in case of we choose for a neural network model, this might be less explicable in terms of the formula when you are going to explain your clients, your students, and everything, what the model has done, what's happened to the features. But it can provide a higher level of accuracy, for example, just as opposite linear regression or logistic regression, which are more explicable but less accurate. So feature engineering is a matter of choice in finding the most suitable variable transformation for the best performance. So when we model, we have dependent and independent variables. So the dependent variable are the response. When we put the response into the model, it shows up as an outcome. And then we have independent variables, which are all our predictors. So if we leave them like that, so they are predictor as provided. If we make a bit of featuring engineering, so we have a feature obtained with a transformation. So other considerations are about bad model reactions. These are due to multicollinearity, which is correlation between predictors, missing values, and irrelevant predictors as well. Okay, so this is the first example in the book. Okay, this is the one I focus on because reading the book, you we go back and forwards to a set of data sets. So I think that's why I've said if you want to split the session, the following sessions within two, so the following chapter within two sessions, because like a bit of time to understand the data will be very important for understanding the process of feature engineering. So the first example here, it's a model with two predictors, just two predictors. We use segmentation data, and this data, it's from an experiment from Kjell et al. 2007, a study on impact of image segmentation on high content screening data quality for cancer, to summarize. And so this is like the image of the cells. And now we are looking at the area and the perimeter. And so we want to predict a class variable using just two predictors. This data set is already split in training and test variables, so we don't do that. We just make a selection. There is a vector named case, and you can select subset the data set within training and test variables. And then what we do is taking these two predictors. So I call it this area and this the other one perimeter. And the objective is to predict the shape. And this can be poorly segmented, PS, or well segmented, WS. Okay, from the class variable. So we are going to make a classification, a logistic regression, okay, with a binary class variable. So here we have an outcome and two predictors. So the outcome, it's a binary class variable, PS and WS. And the predictors are two predictors, A and B, so area and perimeter. Now, yeah, please interrupt me, anything you want to say? Okay, so the book emphasized the fact that simplicity or parsimony is the best. And here is the full list of variables in the set. As you can see. Okay, so we have 61 predictors with 2019 observations. So this is something to think about. So compared to the number of predictors, which are quite a certain number, we have a low number of observations. So now this is the case to make a selections of the predictors, okay? Because otherwise it doesn't, yeah?
As a biologist, can I just say that that's not bad?
Okay.
Like, I know that if you're in big data, that looks really atrocious probably, but I have data that's very similar to this in terms of like outputs of image analysis. And yeah, I'd be lucky if I had 2,000 samples actually like trained and everything. It would take a long time.
Yeah. Okay.
Just some context, that's all.
No, thank you. Any extra additional information, personal experience, it's very important. Okay, so parsimony. So we now reduce the issue, the problem to this situation. We have a class response variable, binary response variable, and two predictors, area and perimeter. Okay.
Federica, just a comment.
Yeah.
I believe that, what we're doing, instead of, contemplating those 61 variables and reducing it to two, I think, the term that they're using right now is called that data budgeting. Okay. Starting with a small sample, okay, maybe of predictors, etc., to try to see, how the model, how do the model reacts to that. So I know that, certain, people in the data science community refer to that as that data budgeting. In other words, selecting first at hand some of the features that you think, intuition, they will be good predictors.
Yeah, thank you. Okay, so the data set is already split, as I said, between training and test set. So all that is to be added is a cross-validation if we want to dig a bit more on the result, okay? And so this is, I've used tidy models to do this little bit about this first example. So I made a cross validation without specifying this stratification, because I don't know if any of you are aware about how to use tidy models or not. But okay, tidy models is about you know, you have this function for making cross validation, just this. Okay, so you have your training and test set, and this is your false with data which are shuffled within 10 folds. Okay, and this is it. It's here, and then we use later. So what we do now, it's a bit of like exploratory data analysis and see the relationship between predictors. So what is the behavior for area, perimeter versus area? So we see that there is a quite not linear, but there is a relationship. So greater is the area, greater is the perimeter, and they are colored by class, so our response variable. So you can see they are well divided. So the bottom side, it's for this is the WS, which is the worst, not very well you know, identified. And this other one it's the best one, let's see. Okay, so now as we have chosen a binary class variable, we need one more thing that we need to check now, that we understand that there is a relationship between the two predictors and they are related to our response. So it's good. So we are doing well. We need to check for the class imbalance of the response variable. Okay, so this will be the first level transformation. This I added myself, maybe a little bit a step forward. So this type of transformation is considered a structural transformation, and we will see more about it later in the book. So if I do a table, I see that PS is 636, while WS is like half of it. Okay, so if I do the proportion, I see that one is 63%, the other one is 37%. So there is a little bit of imbalance. If I set this element on the 37%, which is the bit that has to be upwards in the imbalance within the set, no? I can use a nice step in tidy models. Okay, so this library, the maze, it's an addition to recipes package. So also you have tidy models meta package, which includes recipes as a package. You also need to load this library, the maze, because it does provide this step up sample. Okay, so basically in tidy models we do pre-processing using this recipe function. Instead of doing training or I don't know, like GLM and inside the formula, we use first recipe. So this is the first block of pre-processing modeling, because this way we can do feature engineering. So we can add, modify the recipe, maintaining one model and changing recipes, or maintaining a recipe and changing the model. So we can use this recipe function, which is like formula. Okay, so inside we put the formula on data training, And then we add, we pipe and we add the step up sample. What does the step up sample? Basically balance this class, binary class, okay? We can set the over ratio to 37%. So we want to put the variable upwards of 37%. The one that is lower will be put upwards of 37%, because so it's below of 37%. So it will be upwards based on the proportion of on the overall proportion.
Does it bring
Okay.
it up to 50-50? I've not used that function before.
Not exactly, but it balances a bit. And if you use this and then you pipe, there are further functions which are prep and bake or prep and juice that releases when you do. Let's jump on R and see. Can you see my R?
Yeah.
Okay.
Step up sample.
Yeah, thanks. Okay.
Okay.
Okay, this is what is done to filter the train and test part, because the segmentation data already provide, as I said, this case vector, which is divided within training and test. Okay, so now I loaded everything, and let's run this. And this is the table. And we have this upsample thing. Okay, so now with the MIS, we can do, for example, the first recipe, which is this. And what's happened now, if we take this recipe and we do like bake,
Yeah.
and then juice, because if I do not bake.
Prep.
Prep.
Preppers, yes.
Prep,
juice has been, I thought, deprecated by bake.
But because bake, you need to add new data.
Which is null.
Which is null, yeah.
Yeah. But if you can use juice. So if we do juice,
have it. Yeah.
Yeah, it releases the table with the pre-processing step applied.
Mm-hmm.
Okay. So now if you do, we can do a visualization. So the unbalanced is class, no?
Yeah.
So we do class. We do histogram. Maybe.
Probably bar. Do a bar.
Histogram and
Bar. Do the bar.
Okay. So now this is the result, which is still there is a
just a thought, Federica, the over ratio, if you leave that out, the default aims to balance the classes, to add enough of the minority class to make them the same 50-50. So if over ratio was left out of step up sample, you try that and then do the Geom bar.
Okay.
Is that what you want?
Yeah. Yeah.
Yes.
So it samples the rows that come from that one class
Yeah.
and adds those in to make them equal. Is that right?
Correct.
That's right.
What? Okay. So okay. So I leave that as well.
But it is they're duplicates. So if you think in terms of machine learning, you know what's happening under the hood. Yeah.
Yeah. So, and what's happened with over radio?
Well, if you had a big multi-class problem with lots of categories, you could think about how much mismatch do you want to allow.
Uh-huh.
So you
It's
can define the ratio.
Yeah, to
So it's
maintain
37.
the distance. Yeah.
Yeah, so it's 37%, and you could say, well, I only want to up it to 45, I guess.
Yeah. Okay.
Although I don't know how would you determine what percentage was safe or not? I don't know what you would do there.
Okay.
Could you use tidy modeling to tune the upsampling procedure?
Good one. Yeah. Okay.
I don't know.
I'm kind of thinking like in a logistic regression, it ends up like a weight, and it's not in this book or in the early tidy models writing, but most recently there's been some updates to yardstick to do weights, which maybe is a little more intuitive than making duplicate training samples.
Okay. Okay, so let's go back to where we were. So let's say, let's leave it like that. So let's say that we use, that we want to use this percentage, okay? So the first recipe will be this, with just step up sample. And then we want to make another recipe, which is again, so we go further on step up sample, and we add a step box Cox on all numeric. So the two predictors. Okay. Yeah.
Yeah, in the book, Federica, they explain that they already did an experiment already, using the box Cox transformation, which is the inverse of the original predictor number. And what happened was that transformation increased the model performance, okay, by, let's say, 10%, 50%, but it was significant. So that's what in the real world, usually what you do is that you try to see how skewed those features are. Okay, for example, if there's a highly skewed feature, you should transform it, because most of the time, especially in the linear logistical regression, they expect the predictor to have a normal distribution, a Gaussian distribution. So this transformation helps alleviate that skewed the shape of the data.
Exactly.
Okay?
And we will, sorry.
Right, but to do that, you have to visualize your predictor. Okay, it's not that you're going to do it all the time.
Exactly, we will see that, exactly. So we do this step Cox. That means that we reverse our predictors, one divided by the predictor. So we reverse it. So we are making feature engineering. So basically we transform our two area and perimeter predictors into be the reverse. Okay, one divided by itself. So with tidy models, we can make a logistic regression with this parsnip syntax. We do logistic regression and set engine, and we have specified the model. Okay, so the recipe is the formula with the pre-processing steps. This is the model in itself. So like the LM function, GLM function in itself. So just the function that makes the model function. Okay, so we have the model type and the engine used, because there's different engines that can be used. Now we use a workflow to add the model and add the recipe. And then we fit the workflow on the training data. And then we extract the parsnip and tidy to see the result. So here we see that there is some estimates and p-values about the area and the perimeter. Okay, so let's leave it like that for a minute. So the area, we are not thinking about significance at the moment. And what do we do is to augment, so adding to our original data. In this case, we add to the test the predictions, a vector with the prediction. So our new table will be this. So we have the class, the area, the perimeter, and the predictions. Okay, we have a pred class and the two prediction, a single prediction for the predictors. Okay, if we do a quick confusion matrix with the training and test set, we can see with this model, with this, we have used just the first recipe. So the one with the step upwards, not the one with box cocks. Okay, so for now we are looking just at the first recipe. So we can see there is a bit of difference between the training and the test set. So the test, but not that much, but the test set is a bit lower in guessing the predictions. Right, so if we do a quick visualization, we see that the rock curve for this model is like so and so. Okay, so can be, we want to achieve an higher area under the curve. I may have a question. What is this threshold? That yeah, what is the threshold?
Sure, in logistic regression, that's the cutoff.
Okay.
So usually
So
as a post-processing, you can instead of cutting off at 0.5, which is typical in some contexts, you can change your false positive or your sensitivity or specificity by choosing a different cutoff rather than 0.5. And in many cases you would to avoid either getting false positives or well, especially with your imbalanced data set, right? Recall that you're starting out with something that if your class of interest is the small class, it's not likely you would really want to use 0.5 as your cutoff. And so in an odd way, this can convey both because there's an area under the curve, so the performance of the model, but also that trade-off between sensitivity and specificity. If you change that threshold, just what's kind of funny about using a continuous color scale is you can't really see where the color of 0.5 is. So maybe this graph would have looked a little better if it was in
Yeah, in
say
yeah.
five sequential colors, and then you could see exactly where the 0.5 break is.
Okay. All right. Okay. Yeah.
If-
No, I did it just to, yeah.
If that makes sense, and
Yeah.
and it's in an academic setting where everything's balanced, it doesn't matter. but
Right.
Yeah.
but in life, when you're chasing outliers or fraud or so many things in natural language processing, the cutoff can't be 0.5.
Okay. So I need to dig a bit more about
Federica,
about.
if you can scroll up, you know,
Yeah.
just to make Jean's point a little clear. Yeah, go up. Yep. Okay, here we go. Okay, those two, you know, rightmost columns. No, go up.
Ah, sorry. Okay.
The pred underscore PS, pred underscore WS, those are the probabilities, okay, that the model is calculating. Because right now the cutoff is 0.5, right? 50%, 0.5. So that means that anything less than 0.5 is going to be predicted, right? As a, you know, as the magnetic class. More than 0.5 is going to be predicted as the majority, okay? So if you tweak that, you know, to try to get the most, you know, the most curvature of the RC curve, okay, the best balance between specificity and sensitivity, then, you know, you will have a different confusion matrix. In other words, the results will change, okay? But right now the default is 0.5.
Okay, so now we want to compare this result with the other recipe, with the box Cox step, and see what's happened. So to do that, I used a workflow set. So in this way, we can add the two recipes in the pre-processing things. Inside, you have the two recipes and in a workflow set. So I run the model with the false. Here I use the false, okay, for the resamples. Yeah, in the workflow map. I go a bit forward about this because I want to, now we have 5 minutes, but we will be back on these things, okay? So the model run quite fast, and these are the results. And if I do a ROC curve of both recipes, you can see that there is like an improvement with the inverse unit logistic. So that means the box Cox transformation. So this is feature engineering. Then you compare and decide which recipe is the best. So which pre-processing step you want to keep to do your modeling. Or for now we have examined just two steps and two predictors, so very basic, but it's enough for you to see that there is an improvement without changing the type of model. So the model is the same. We didn't change anything. The only things that we change are we have transformed the predictors. Okay, so to conclude, some important concepts are to mind ourselves is overfitting, other techniques that uses supervised and unsupervised, featuring, and then model bias and variance, and experience and empirically driven modeling. So basically, generalize the main boundaries. The risk of overfitting the model is always challenged by anomalous patterns new data can hide. So you might do everything good all following all the procedures, but then you have some anomalous data in your new data, and the model doesn't fit properly. So, for example, I've put a list, like a to-do list, okay? If you have a small number of observations, you need to double check compared to the number of predictors. If you use a low bias model, remind yourself you can have an higher likelihood of overfitting. Then if you use supervised analysis, you can use it. For example, the book tells about a group of researchers that were using supervised analysis for detecting predictors' significance. So basically, they didn't want to use a response variable, but they have taken a response variable and carried on a supervised analysis to identify the relationship within the predictors. And this is another technique that can be used. No free lunch theorem. So knowledge is very important. So if you don't know about the topic, about the things, that will be a problem. Okay, so knowledge it's important. Then the variance bias trade-off says that low variance belongs to linear and logistic regression and partial least square, while high variance it's for trees, nearest neighbor, and neural networks. Then again, bias, what is it? Here I stopped a bit in the chapter, because bias says it's the ability to achieve a high level of estimation. I think it's the level, so it's the level of ability. So, but what's happened if you have high bias? So the level of ability is not lower. So that there is something like tricky on this thing. So the bias is the best. If the bias is high, the model is not good. If the bias is low, you have a better model. So then you need to think about relevant predictors, irrelevant predictors. So like make a selection. This is in general, we use this to-do list within all book. So select for irrelevant predictors. And then there is like this discussion about experience. It's better than experience-driven data, so selection is better than data-driven selection. That's not said. So sometimes it's better to trust the data more than experience. So you can gain some suggestions from the expert, but you mind your data first. And then big data doesn't mean better data. Unlabeled data, this is your case maybe, Brandon, so can improve autoencoders modeling. So they can use unlabeled data to test autoencoders. And then there is a compensatory effect. So we now up the time, but so to you know, there's few more things about to mention. For example, that I found interesting when if you find like supervised selection method can be divided to wrapped methods or embedded methods. So wrapped methods are external selection of features, backwards and stepwise selection, while embedded methods are the natural selection of the predictors. For example, when you apply a tree model, a decision tree. So this, and then the unsupervised selection is variable encoding, such as dummy variable or indicated variable. So this is the modeling process. So you do exploratory analysis, a summary, some correlation. Then you evaluate which type of model you like to use. If there's tuning parameters, because it's a complex model, you use model tuning. Then again, a summary and see what are the results and some other exploratory data analysis. Then you check the residual analysis for systematic issues. And then you see now your model has released some result. You need to do more transformation on your data. Maybe yes, maybe no. So mind that you can do more feature engineering at this point. And then again, finally, model selection, final fit, the final fit, and extrapolate the predictions. So this is what I have extracted from just the first introduction of the chapter, which is immense world, very interesting. On top of this, there is a more complex example, which is predicting ridership on Chicago. And at this point, this is the data set. I've just put the data set because we are going to use this data set through the whole book. So it's important that we have a look. But I have found this nice presentation. So I put in the chat. This is from Max Kuhn, and it talks about this data set. So you might want to have a look at it, maybe. Wait, sorry about that. I was searching for the chat. Okay. And I think it's all, you find the notes already up. I've had a few more modifications, so I'm going to push them again with the addition. And so this is a nice presentation. You can have a look, and these are the data for the more complex example. Oops. Okay, so it explains the different steps that can be used for this type of data set with tidy models. And what else? I think it's all. So now I've lost my, I stopped sharing. Okay. Yeah.
Thank you.
I add the little bit more resources that I've added at the bottom of the notes, so for you to have a look at, because they are quite interesting. And it's all. Yeah, there you go.
Cool.
Cool.
Okay,
All
see you in a week.
Yeah. Thank you, everyone.
Thank
See
you.
you
Thank you.
next week. Bye.
Bye.
Bye.